Hey, AP Chem. Welcome back to equilibrium in terms of precipitation. We're going to talk about the second half of it today, which is the flip reaction. So yesterday we dealt with this idea of solubility, right? Which is when the salt dissolves into ions. Today we're kind of going to do the flip of that, where we have ions that are forming a salt. So that is what we call precipitation. When we have these ions present and they come together to form that solid, and that solid sinks to the bottom or floats around like a little cloud that you have to filter out of your aqueous solution. So that's precipitation. Now, even though we're dealing with precipitation, remember, we're still dealing with the equilibria, and the equilibria is still going to be dependent on KSP. So it's really important to remember that when you are given the KSP of something, you're dealing with this reaction that is solid goes to ions, right? And then you have this little double arrow that allows you to go both ways. So it's going to be the reverse arrow that gives us the precipitation reaction, but you still have to write your reaction in this way in order to match the KSP, because we want the ions for KSP to be in the numerator, not the denominator of your KSP fraction. If you wrote the reaction in the reverse way, you would have those ions in the denominator because they'd be reactants, right? So we still want to be careful to write our reaction the same way. Okay, so when we're dealing with precipitation, the way we're basically going to deal with it is in terms of K. We're going to look at it in terms of K and Q. So think about this idea of equilibrium, right? If we are at equilibrium, that means our forward reaction, which is dissolving, is equal to the rate of our backwards reaction, which is precipitation. So at equilibrium, we have dissolving and precipitation happening at equal rates. So whatever is present isn't going to have a net change. You won't have a net amount of solid disappearing. You also won't have a net amount of solid appearing. Those rates are equal. But just beyond equilibrium, like the femtomole past equilibrium, you're going to have precipitation occur. So basically, we're going to use that line of equilibrium to say, okay, this is when precipitation starts. Or if we're looking at the opposite reaction, this is when dissolving starts, because any super small increment on either side is going to push that reaction forward. Okay, so when we're dealing with this idea of if precipitation will occur, we're going to look at where we stand now, right? We're going to look at that same law of mass action fraction where the amounts are presently, and that's what Q is. Okay, so let's think through this again. If Q is greater than K, right? Q, that fraction, those products have to get smaller in order to reach equilibrium. So that would be the reverse reaction. If we need our concentration of ions to lessen in order to get back to equilibrium, that means our ions have to precipitate out. Our concentration of ions is going to decrease because they're going to stick together and form our solid, right? So if Q is greater than K, we're going to get precipitation. Let's think of it in the other way. What if Q is smaller than K? If Q is smaller than K, then those ion concentrations need to get greater in order to hit equilibrium. And so in order for the ion concentrations to get greater, our solid has to fall apart into more ions. And as we build those ion concentrations up, then our products multiplied together, our ions concentrations, will increase and we will hit equilibrium. So that would be describing dissolving. So if Q is greater than K, precipitation is going to occur. If Q is less than K, dissolving is going to occur. All right. Okay, so let's look at this math behind this. All right, a solution is prepared by adding 750 milliliters of 4 times 10 to the negative third molar CeNO3, okay, to a volume and molarity of KiO3. So will CeIO3, this is going to be our reaction, to give us the KSP, will it precipitate from this solution? Okay, so we have a lot of things present, but the reaction we're going to deal with is the reaction we care about. So pause here, see if you can write a reaction. The one we care about is going to be selenium iodate, CeIO3. When it falls apart, we'll get CeIO3 minus, and we'll get 3 of these. Okay, will it precipitate? So in order to figure that out, I need my initial amounts of Ce and IO3. So let's figure out what those are. All right. Ce is going to come from this compound. So here's the information on this compound. Let's figure out what our concentration is, because remember, our concentration is not just 750. We're taking 750 milliliters that contain selenium nitrate, and we're adding it to 300 milliliters of KiO3. So in the end, my selenium is floating around in 1 liter and 50 milliliters, something like that. 1.05 liters. My selenium's floating around in that solution, and so I need to know the molarity in that solution. So let's figure out how many moles of selenium we have, and then figure out the molarity in that solution. This would be a good time to pause and see if you can beat me there. So 0.75 liters of selenium nitrate, 4 times 10 to the negative third moles per liter of selenium nitrate will give me the moles of selenium nitrate. Now for every 1 selenium nitrate, I'm going to get 1 Ce3 plus. So the molarity of selenium nitrate will be the same as selenium. Now that amount of moles is going to be floating around in 1.05 liters. So that will get me my molarity of the selenium ion in my complete solution. All right, let's do the same thing for KiO3. All right, so here's my information. And then again, for every 1 KiO3, I'm going to get 1 IO3 minus. So they'll have the same molarity. So 0.3 liters times 2 times 2 to the negative 2 moles per liter. And that's going to be IO3 in my new solution of 1.05 liters. Okay, let's do the calculations and figure out what those are. All right, I have 0.002857 moles of this. I have 0.005714 molar of this. Okay, so those are my initial amounts, and I want to know what my Q is. So I'm going to take my KSP, my KSP is going to equal selenium. And then I have IO3 minus, and that has to be cubed. So I'm going to get 0.002857. I'm going to run out of space. Let's try that again. So for my Q, I'm going to get 0.002857. For my selenium, 0.005714 cubed. For my iodate. Okay, so that we're going to calculate. And I get 5.3 times 10 to the negative 10th. Okay, so that's my Q compared to my K. They're pretty close, but my Q is slightly larger than my KSP. And so precipitation will occur. Will precipitate form from the solution? Yes. It will precipitate until the Q is equal to the KSP. Okay, so looking at this, the first thing you need to be able to do is write that reaction, right? You're given a ton of compounds. You really need to think, what do I care about? What's the reaction that I care about? Turns out you don't care about nitrate ions or potassium ions. They're not of interest to you. Also, because your volume is adding together, your volume is changing, you need to calculate new molarities. You can't just use the old molarities that you have when they were alone in their bottles, right? And then this problem boils down to comparing where we're at initially, which is the Q, to where equilibrium occurs, which is the K. So we're going to compare those two. A lot to keep track of, but we're pros at this point in time, right? We can handle the change in context. Let's look at another one. Okay. What are equilibrium concentrations of Pb2 plus and I minus in a solution formed by mixing volume and molarity of PbNO3, volume and molarity of NaI? What are equilibrium concentrations of these things? Okay, so again, we have lots of compounds here, PbNO3, NaI, and then they give us the KSP of PbI2. So pause here, see if you can write a reaction for what we care about. The thing we care about is PbI2. So you're going to get Pb2 plus, I minus, and we'll get 2 of those. Okay, so again, we want to know equilibrium concentrations of these things. Let's figure out what we have initially. I should probably space those out because we're going to have to do another calculation. Plus 2I minus. Okay, so I have 0.1 liter, 0.05 molar, PbNO3. That'll give me the moles of Pb2 plus, and it's 1 compound to 1 lead ion, so that's nice. Okay, now I have 0.2 liters times 0.1 molar. NaI, again, 1 compound to 1 I minus. Okay, so that'll give me the moles of the iodide. Now I want concentration, so I'm going to divide by the total volume. 100 plus 200 equals 0.3 liters, 0.3 liters. Okay, so now I need my calculations of these. All right, initially I'm going to get 0.0167 molar Pb2 plus and 0.067 molar I minus. Okay, now what is going to happen here? They don't give us an initial amount of our solid, which it's not going to affect K anyway. So let's figure out what our Q is. ions. If I take 0.0167 times 0.067, I got to remember to square that. I get my Q, and at this point in time, my Q is greater than my KSP. So I'm going to precipitate this. This is going to precipitate out because here's my KSP. Okay, I know I'm going to precipitate this out. So these, just like when you add a strong base to a weak acid, or you add a strong acid to a weak base, and it's going to push forward until completion, and then we swing back to equilibria, right? We're going to treat this problem the same way. We're going to treat it as if it goes to equilibrium, and then we're going to, goes to completion, and then we're going to swing back to equilibrium. So let's do that. Let's go to completion here. So if I were to go to completion, I'm going to react all of my PbI2, and then remember, this is going to react same amount but doubled. Okay, so let's figure out what we have left. Here we have 0 left, and here I'm gonna have 0.033 repeating left. Okay, so if I went to completion and I just precipitated everything out that I possibly could, then I would have some iodide left over and no lead. Okay, so at this point in time, conceptually what has happened is I started with all lead and iodide ions, and some of them came together to form lead iodide, right? So now at this point in time, I have solid lead iodide floating around. I have the iodide ion floating around, but I don't have any lead ions. So at this point in time, in order to go back to equilibrium, some of my lead iodide has to redissolve to establish that lead ion again. Okay, so I'm completely out of room here. So let me erase what I just drew, and I can do it over here. Okay, so we're going to swing this forward. We know we just went this direction where we formed ions together to form solid. So we have some lead iodide that we can now dissolve, right? So at this point in time, I'm going to have the same equation. I'm just rewriting it because I ran out of space. I have no lead ions. I have 0.0333 molar, and I have some solid. So now some of that solid's going to dissolve, and I'm going to gain some lead ions. If I gain X of the lead ions, I'm going to gain 2X of this. So my equilibrium concentrations will be some amount of lead 2 ions, which is X, and then 0.0333 plus 2X of my iodide. Okay, now, just like with a weak acid or a weak base, I'm going to plug that into my K equation. So KSP, which they give us, is going to be equal to X times 0.0333 plus 2X. Just like with weak acids and weak bases, I'm going to assume that the X amount is going to be super small. So anytime it's added or subtracted to a number, it's not going to make a significant difference to that number. So I'm going to get X times 0.0333. And now I can solve for X. So I take my KSP, I divide by 0.0, and sorry, this has to be squared, because my KSP is going to be lead iodine, lead ion times iodide squared. Okay, can't forget that squared. So KSP divided by 0.0333 squared is going to be equal to 1.26 times 10 to the negative fifth. Okay, so my lead concentration is that 1.26 times 10 to the negative fifth, because my lead concentration at equilibrium is just X. My iodide concentration is going to be 2X plus 0.0333. That X isn't going to make a significant difference, so my iodide concentration is just going to be 0.0333 molar. Okay, so this one was a little bit more complicated, right? We really had to search through this conceptually. We had to think about how just the ions were present, the ions came together and made a solid, and then some of that solid had to redissolve to finish equilibrium, or to establish equilibrium. So it was a little bit more complicated, but a really similar idea to a strong acid or base pushing to completion and then swinging back to equilibrium. Again, we used our Q to figure out which way initially we're going. And then don't forget, on those KSP equations, the coefficients matter, right? So you have to cube or square or whatever. With the exponent, you have to use the coefficient as that exponent on that K. And it shows up in the K equation as an exponent. That coefficient is also going to show up when we're dealing with change, like over here on our equilibrium where we change to 2x. So don't forget about the effect of that coefficient. It does make a really big difference. Okay, one more practice problem. Let's see what this one is about. Solution is prepared by mixing a volume and molarity of magnesium nitrate in a volume, here I'll switch colors, a volume and molarity of sodium fluoride. Calculate concentrations of magnesium and fluoride at equilibrium with a KSP of MgF2. Okay, on second thought, this seems like a repeat of the one we just did. So let's do this one together in class as practice. Okay, this one's on selective precipitation, so slightly different context. Let's do this one together now. All right, a solution, we have a molarity of copper. We have a molarity of lead. If a source of iodide is added gradually, will PbI2 or CuI precipitate first? So which one will precipitate first? Specify the concentration of I minus necessary to begin precipitation of each salt. Okay, this one is kind of an application. Would be a good place to pause and see how far you can get on this question by yourself. So if I am going to compare the precipitation of two different salts, I need two different reactions. So PbI2, we just did that reaction, plus 2I minus. And then we have CuI minus. Okay. Now they give us molarities of Cu2 plus. So I have 1 times 10 to the negative fourth molar and 2 times 10 to the negative third molar. And we want to figure out the concentration of I minus. Okay. And I have Ks. So to set this up, I need to figure out what my concentration of I minus is going to be. And again, I can use that equilibrium marker as like the place where equilibrium or precipitation is going to start, because remember, a minuscule amount past that equilibrium will start precipitation. Okay, so we're going to use equilibrium as kind of our starting point. So let's figure out where that is. Okay, so KSP on this one is going to equal 1 times 10 to the negative 8, and that equation is going to be PB raised to the first, iodide raised to the second. Okay, this one, I'm going to have my KSP. It's 5.3 times 10 to the negative 12th, and that's going to equal copper 1 times 10 to the negative 4th, times iodide raised to the first. Okay, so I'm just going to solve for iodide in both of these cases. Okay, so if I take my KSP and I divide by lead, then I have to square it, and I get a concentration of iodide, which is equal to 0.00265 molar. All right, same thing over here. I take my KSP, I divide by copper, and I get an iodide concentration, which is equal to 5.3 times 10 to the negative 8th molar. Okay, so let's think about this conceptually here. So as I gradually add I2, I need to add 5.3 times 10 to the negative 8 molar of iodine in order to start precipitation of copper iodide. And I need to add 0.0265 molar of I minus in order to get this to precipitate out. So this is the smaller amount here. If I start from 0, I minus, and add slowly, I'm going to hit this amount first, which means copper iodide will precipitate out first. I need less of the iodide to precipitate out. It's like saying, if you were going to make someone happy by giving them money, and it took 50 cents to make my child happy, but it took $20 to make a high schooler happy, who would I make happy first? If I start with $0 and slowly add cash, right, my child is going to be happier first because it takes less money to make them happy. That's kind of the same thing here. It's going to take less iodide to start precipitation of copper iodide, so that one's going to precipitate out first. Okay, so slightly different context. We're comparing two salts here. This one's called selective precipitation. And again, you really have to understand the context of what you're looking at, not only the math, right? Okay, so we got some fun facts here. We got some practice problems. And then the last idea here is just complex ion equilibrium. So let's go back and look at that fun fact. The sulfide ion is often used to separate metal ions because metal sulfide salts differ dramatically in their solubilities. The ion is also basic, so it can be regulated using pH. So that would be a application of lab fact, a random question they might ask you on the test, or like a design of a lab. If they ask you to design a solubility lab, knowing that the sulfide ion is a good one to distinguish between solubilities could help you design a lab. Okay. All right, we'll do that practice together. Complex ions, there's a whole section in your book about complex ion equilibria, about dealing with these calculations. So you don't necessarily have to be able to do the calculations inside of complex ions. You really just need to deal with those two parts that we just went over. Day 1, which was dealing with stuff dissolving, day 2, which is dealing with that precipitation. But it is good to be aware of what a complex ion is. And we've actually talked about these at a couple different points in the year. In the very beginning of the year, we talked about hydrates and complex ions. When we talked about acids and bases, again, we talked about complex ions there. So let's just they show up on the test once in a while, but they're a lot like organic compounds where you don't really have to propose any use for them. You don't have to name them. You don't have to propose the compound, but they will sprinkle them into problems. And so just being able to see it and not panic is the goal here. So let's kind of read through this so you're a little familiar with ionic complex ions. And when you see one, you're not going to panic, right? Okay, so what is a complex ion? It's going to be something charged, usually a metal, and usually a high charged metal, like aluminum 3+ or lead 4+. Those are common ones that we see in a complex ions. They don't always have to be highly charged, but a lot of times they are. And then that metal ion is going to be surrounded by ligands, and the whole thing is going to be charged. So if you look at our examples here, notice all of them, boom, 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 all of them always charged, right? So a complex ion is just that. It's always going to be an ion. And this ion is composed of a metal ion and ligand. So what is a ligand? It is going to be a Lewis base. And remember, Lewis bases are things that are electron rich. They have electrons to donate. So if we look at this, we see the metal is attached to things like water or ammonia, and water has 2 lone pairs of electrons, so very electron rich, can easily act as a Lewis base. Same thing with ammonia. Ammonia is going to look like this. Again, has an extra lone pair. It's going to be electron rich. Okay, so the number of these Lewis bases that are attached, that number is going to be called the coordination number. So is that metal attached to 6 waters or 4 waters? That number is called your coordination number. Now, usually you're going to get coordination numbers of 6, 4, or 2. Those are the most common, but you can see others. You can see here in this complex ion with silver, it has a coordination number of 1. So they're possible, but 2, 4, and 6 are going to be most likely. Here you can see a picture of what a complex ion structure kind of looks like. And again, it's going to be governed by forces rather than super strong bonds. Okay, last thing to know about complex ions, their Ks are usually pretty large. So they're going to, so for example, we see a couple of reactions down here with the metal ion. You have that Lewis base forming a complex ion, and the K here is 2.1 times 10 to the third. That's a pretty big K. So it's going to form in pretty substantial amounts. Also, notice that the metals add those ligands one at a time. So silver is going to add 1 ammonia that has a specific K, and then that complex ion will add a second ammonia in a second reaction with a second K. So they're really similar in that way to polyprotic acids that protonate one at a time. These are going to add on those Lewis bases one at a time. Okay, so now you know all you need to know for complex ions until you go and study them specifically by themselves in your doctorate work. And when you see them on the test, you're going to be like, oh yes, complex ions. I know you. We are friends. Let's do this. And you're going to be super calm and you're not going to panic at all. Okay, so that's basically chapter 16. We'll get back together. We'll practice some of this stuff. Definitely let me know what your questions are. I will see you in class.